Hello everyone, I am Abhinay Reddy Naini, affiliated to Spire Lab, Electrical Engineering Department, Indian Institute of Science, IISc Bangalore, India. Today I will be presenting about our paper titled Whisper Active Detection using CNN LSTM based attention pooling network trained for a speaker identification task. So these are the outline of my today's presentation. First, I'll be introducing the problem. Then I'll discuss about the proposed approach. Then I'll give details about the data set. Then I'll explain about the experiments and results we got. Then I'll conclude with a summary. So let's begin with the introduction. So voice active detection is a process of identifying speech region in a noisy audio file. As I shown here, for a given speech signal input, a typical voice active detection block try to identify the speech region by avoiding the noisy region, and which is a very important pre-processing step in almost every speech application. So to give detail about whisper speech, which is another natural way of generating speech with options of vocal fold vibration. I'm sure everyone might have whispered at least once in our lifetime, which typically comes in private conversations as well as pathological situations such as laryngectomy. So it is very challenging to handle whispered speech in typical speech-based application. That is mainly due to the absence of glottal vibration. So this illustration shows a temporal and spectral comparison of the neutral speech and whispered speech. That is, this was easy for us spoken by a woman speaker. We can see that the whispered speech spectrum is significantly different than that of the neutral speech spectrum. Particularly, we can see there's the absence of pitch in whispered speech spectrum as well as a shift in lower order formants upward compared to that of the corresponding neutral speech spectrum. So these are the main difference in whispered speech spectrum compared to that of the neutral speech. So coming to our this paper's problem, that is whisper active detection. So which is nothing but identifying whispered speech region in a typical noisy audio file. So it is well shown in the literature that a typical voice active detection performs poorly in the unvoiced region compared to the voiced region. So due to the unvoicedness of the whispered speech, it is more challenging to detect the whispered speech in a noisy audio file compared to that of the voiced neutral speech. So that is also shown in this above illustration, that is a spectral comparison of the neutral speech and whispered speech. And the next row is which are corrupted with the additive white noise. We can particularly see in this noisy whispered speech spectrum, recognizing speech region compared to that of the noise region is more challenging compared to the corresponding neutral speech spectrum. So there are several features have been proposed to handle whisper active detection. Among this, using long-term log energy variation of subband signal, that is LT-LEV, is known to perform better than existing features. So in this, the optimal subband sequence is obtained for each noise in the training phase. In the testing phase, these optimal subbands are used to filter the signal. Then the LT-LEV of the filter signal is used for bad decision. Even though this method performs well, there are several limitations to this method. One is it can only be used in scene noise condition. And the another limitation is that because of the supervised training of the optimal subbands, LT-LEV requires annotated data indicating the whispered speech region. So this will be a problem when we have a larger whispered speech corpus for training. So we need to have entire training data to be annotated with the speech region. So let's see how we handle these limitations in our proposed approach. So in this paper, we proposed a whisper active detection using CNN LSTM model. So in this presentation, we call it as APW, that is attention pooling weights based method as short. So to give a brief about our proposed method, in any typical speech-based networks, the attention block weighs the speech region higher than the noisy region, which happens both in neutral speech as well as whispered speech. However, in particularly whispered speech-based networks, we observed that these weights could be useful in making bad decision. So to give detail about the proposed method, so for a given speech signal, we computed the log filter bank features. Then these features are given as an input to the CNN LSTM network, where the weights coming from the LSTM attention block weighs the CNN output, and further this given as an input to the classification network. And this entire thing is trained using categorical cross entropy loss function for a speaker identification task. In the test time, for a given speech signal, we compute the weights of LSTM block using the trained LSTM block, and by applying a post-processing on these weights, we make a valid decision. So this below block shows a post-processing method proposed in this paper. So to give detail about the post-processing method, so for given LSTM weights, we apply a median filter first on the weights, and after that, we give that to the two parallel blocks we shown here. To give detail about this, the first block, that is binary quantization with threshold N1, we try to see how many weights are above than this particular threshold. And the moving average window computes the number of weights higher than that particular threshold. And by applying a threshold on those number of weights, we make a valid decision. So the second parallel, which is also very similar to the first parallel, however, we decided that the first threshold should be little bit lower compared to the previous threshold, but the density threshold should be higher compared to the previous threshold. So finally, these two whisper decisions are combined to make a final VAD decision. So to give details about the dataset, first we consider double spy dataset, which contains 1 or 2 speakers, each speaking 50 sentences in whisper mode. Even though all the datasets we consider have both neutral as well as whisper speech parallel recording, we consider only whisper speech data for these experiments. So double spy dataset, which has been recorded using 5 recording devices parallelly. However, for this experiment, we considered only 2 recording devices data. Those are Zoom recorder as well as data recorded using Moto G5 mobile. So Zoom recorder data is used for the training, and data coming from the Moto G5 mobile is used for the testing. So along with the double spy dataset, we consider 2 open datasets. Those are WTMIT dataset and change dataset. So in the WTMIT dataset, we have 48 speakers, each speaking 450 sentences, both in neutral and whisper mode. However, we considered only 50 sentences from whisper from the WTMIT dataset. And coming to the change dataset, we considered 36 speakers, each speaking 37 sentences in whisper mode. To have experiment with different noise conditions, we considered 8 different noises from the NoiseX92 dataset. Among these, 4 types of noises are used for the training. Those are ping, mission, factory, and restore engine noise. And the other 4, such as white noise and speech bubble, that is SB, machine gun, MG, high frequency HF noise for the testing. To give details about the experiments and results, we considered 2 experiments to mainly to see how both the methods perform when they are trained with the clean speech data and using clean speech data augmented with the different training noise types. So in the first experiment, we have used only clean speech data for the training. However, both the proposed method and the baseline method are tested using 4 testing noise types. In the experiment 2, along with the clean speech data, we have augmented the clean speech data with other 4 trained noises. And similar to the experiment 1, we have also trained both the proposed method and the baseline method using 4 testing noises. As I already mentioned, baseline method, one of the limitation is that it cannot be tested on unseen noise. So to have a fair comparison, we computed the optimal subbands for all the training noise types. In testing, we computed the VAR results for all these optimal subbands for all, and we retained only the best performing results to have a fair comparison. So this slide shows the training data we used for the experiment. So in the experiment 1, we have used 80 speakers from the double spy dataset with 40 whisper speech utterances from each of them. The remaining 10 are kept for the testing. And as I already mentioned, for training data, we have used only Zoom recorded data, and Moto G5 data is used for the testing. So along with the above double spy data, 40 whisper speech utterances from each of the 48 speakers of the WTMIT database also used for the training. And remaining 10 whisper speech utterances from the WTMIT is used for the training of post-processing block parameters, which I already mentioned about those 4 thresholds which we need in the post-processing block. Coming to the experiment 2, we have used the same data as experiment 1. However, we augmented this data using 4 different type of training noises at -5, 0, 5, 10, 15, 25 dB SNRs. We have considered different SNRs for the training and testing to see how both the methods perform in unseen SNR type of condition. Coming to the testing, that is, we considered 5 different test cases, mainly to see how these methods perform in seen and unseen subject and seen and unseen environment type of conditions. So in the first test case, that is 1A, seen subject and environment. So we consider remaining 10 utterances from the 80 training speakers of the double spy. So the subjects and the environment will be same. In the test case 1B, that is unseen subject and seen environment, where we consider 10 utterances from the remaining 22 speakers of the double spy dataset. So the speakers of the testing will be different than of the training. In the test case 2, unseen subject and environment, we consider 10 utterances from the 36 speakers from change database. So for the testing, we have used completely different data set than the training. So that speakers and the environment will be different than the training. In the test case 3, that is seen subject and unseen device, we have used 10 utterances of 80 training speakers from the double spy dataset. However, these are coming from the Moto G5 recording device. So the recording device is different than of the training, even though subjects are same. In the test case 4, that is unseen subject and device, here we consider 10 utterances of 22 speakers from the double spy recording dataset, and which are recorded using Moto G5 mobile. So that speakers and the recording device both are different here. So to see whisper active detection evaluation metric, we considered a cumulative accuracy, that is ratio of the number of correctly classified frame to the total number of frames to measure the performance, which is denoted as CWAD in this presentation. These are the results we got it from the both the experiments. In the first slide, that is first experiment. Here we have used only clean speech data for the training. We can see that there are 4 different columns which indicating the different test type noises, and we can see 5 rows here, that is 1A, 1B, 2, 3, 4, which indicate for the different test types. And here the blue indicate the baseline, that is LT-LEV, and the yellow indicate the proposed method, that is APW. And we can see here -10, -5, 0 to 30. These are different test SNRs which are different that of the training. So we can see that in almost all test cases, the proposed method performs better than the baseline. Particularly in test cases 3 and 4, where the method are tested using the data coming from different recording device, the proposed method performs significantly better than the baseline method. A major difference in performance is observed for the machine gun noise. It seems like LSTM block is trained to avoid short burst type of noises such as MG. Due to this, we observed a significant improvement in the baseline. On the other side, a lesser difference in performance is observed for the babble noise, where the baseline also performed reasonably well along with the proposed method, particularly for the test cases 1A and 1B. These are the results coming from the experiment 2, where we have used, along with the clean speech data, we have augmented the clean speech with the other training noises. We saw that even though baseline performance is improved compared to the experiment 1, which is not significant compared to the improvement in the proposed method. Particularly in test cases 3 and 4, the proposed method performance significantly improved, even reaching up to 80% in -10 dB SNR type noise condition. So this is a performance comparison of the baseline and proposed method. So this illustration shows performance comparison in both the baseline and the proposed method in different different SNR level with data is corrupted. In the first row, time varying speech signal with red line indicating the whisper speech region, and the second row indicating the corresponding spectrogram. And the third row, we can see the weights coming from the LSTM block. Even though they looks like a random, but we can see that wherever the speech region is there, the weights tend to be higher. Wherever the speech region is not there, the weights tend to be lower. And the fourth row, we can see red line indicating the ground truth, and the black line is showing the VAD decision coming from the baseline. And the fifth row, red line indicating the baseline, and the black line coming from the proposed method. So here we can see 5 utterances in this considered sample. The first 2 utterances are corrupted using 0 dB SNR noise, and the third utterance is corrupted using -5 dB SNR noise, and the fourth and fifth utterances are corrupted using -10 dB SNR noise. That is decreasing order of SNR. In -10 dB SNR, we can see that even though proposed method may not perform well, but which perform significantly better than the baseline. And even in the higher SNR case, where we can see that the proposed method is more closer to the ground truth compared to the baseline. So to conclude, we showed that robust VAD can be achieved by attention pooling based network, which is trained for a speaker classification. We also showed that the proposed method is robust toward the varying noise and recording device conditions. And the major advantage with the proposed method is it can be trained on limited annotated data. That is, we only need annotation for approximately 10% of the training data that is used for computing the parameters in the post-processing block. Remaining training data, we only need the speaker labels, which will be major advantage when we have a larger whisper speech corpus for the training. For the future work, we want to observe how the proposed method performs when trained for other speech tasks such as gender classification. So authors thank the Department of Science and Technology, Government of India for their support in this work. If you have any questions or suggestions, please write to us at spirelab.ee@iisc.ac.in. Thank you.